Hi, how's it going? How's differentiation going? Hope it's going well for you. Hope you're enjoying it because you're going to need to really enjoy it if you'll get through the 2-year course that you're studying. Okay, so there's plenty of differentiation to come. So I'm going to talk to you today in this video about second order derivatives. So what are second order derivatives? Well, a first order derivative is when you differentiate for the first time. So example, if y equals 2x squared plus 5x minus 3, then a first order derivative would be this. dy dx is equal to, and that will be 4x plus 5. Well, a second order derivative is when you differentiate for the second time. So you differentiate this, okay? So the way we say that is d2y dx squared, and we write it like that with the 2 in between the d and the y. So d2y dx squared. So why do we say it and write it like that? I'll explain in a minute. But when we differentiate this again, we're going to get 4. Okay, so that's effectively what it is. So why do we say d2y dx squared? Well, let me just write down the expression again. 2x squared plus 5x minus 3. Another way of saying let's differentiate that expression is to write this. d dx of this, because we need to formally say what we're differentiating with respect to, okay? Because you might have other letters and variables involved, okay? And we're differentiating with respect to x. So differentiate this expression in brackets with respect to x, that's what d dx of this means, okay? It's just that when it's given in terms of y, of course what we're actually doing is we're finding d dx of y. And of course we just write that as dy dx, okay? So this is just a different way of actually saying it, a slightly more formal way of saying it if you want. And now dy dx is an abbreviation, a simplified way of writing it, okay? So when we find the second order derivative, we're differentiating again, we're finding d dx of this. And that's written like this, you see, d dx of dy dx, okay? That's what we're actually doing, okay? And I don't really like doing this little bit, but it kind of helps to explain what's going on. If we expand the brackets like algebra and treat these like fractions, as I said, I don't really like doing that a little bit because that's not, strictly speaking, what differentiation is all about. But if we did do that, you'd have d times y, which is this, okay? And on the bottom you have dx times dx, which is dx all squared. We write it like this, we don't use the brackets, okay? But the reason we say that as 2 is because we're differentiating for a second time. It's a second order derivative. So dy dx, the first order derivative, and then d2 for the second order derivative, d2y dx squared, okay? So that's why it's written like that, okay? You don't need to know that, it's just I thought you might find it interesting to know. That's the reason why it's written as it is. With the fx notation, that's slightly simpler though, okay? Let me give you another example. With f of x, let's just make up another one, so let's give it a cubic this time. So 4x cubed minus 12x squared plus 3x minus 7, okay? When we find the first order derivative, you just put in the 1 dash to represent the first order derivative, differentiate for the first time, so that's going to be 12x squared, subtract 24x plus 3, and then you've probably guessed it by now, because of my hint I gave you earlier, for the second order derivative, you'd put in 2 dashes, f double dash x, or f double prime x, okay? So differentiate for a second time, you get 24x, subtract 24, okay? And then that's it, okay? That's what second order derivative is all about. That's all you need to know really for this unit, okay? But I want to give you a little bit of an insight as to why we're interested, because you might think, well, that's very good, but why are we doing this? You should really be asking that question throughout your studies, really, you know, why are we doing this? I'm hoping as you go along, things are explained enough to you. So you should be aware of why we're doing this. Why do we find dy dx? It's to find the gradient at any point, isn't it? Okay. Well, let's just look at our expression here. I'm just going to rewrite it in its factorised form. So that'll be 2x minus 1 x plus 3, let's just check that, 2x squared minus plus 5x minus, yep. And if we draw a sketch of the graph, what's that going to look like? So x-intercepts at half, negative 3, so here we go, and let's just draw a parabola, shall we? There we go, so negative 3 and half, so that's the curve there, and as I said, finding dy dx enables us to find the gradient at any given point. So for example, if if my pen represents a tangent, okay, then at that particular point there, the tangent looks like this, and we can work out the gradient of it, okay? And the gradient changes as it goes along, okay? So my pen there represents the tangent. You see the gradient is always changing, okay? d2y dx squared is how the gradient is changing, okay? It's how the gradient of the tangent is changing as x changes, okay? So let me just explain it visually by this. How is the tangent line changing? Okay, how is the tangent line changing as I go from left to right? Okay, well, you can see the tangent is always sloping downwards, so it's always got a negative gradient between here and here. Let's just put in that point there, because that's a crucial point, that is, the minimum point. Okay, later on you'll be doing more with finding minimum points and maximum points. Okay, so the gradient, notice, is always negative, okay, from here to here, 0 at the bottom, the midpoint, and then it's positive here. So that's all about the first order derivative. We can see when the gradient is going to be negative, it's going to be positive when it's going to be 0. Okay, that's a bit of an insight into what you'll do later on with finding minimum and maximum points. The second order derivative is how the actual tangent is changing. Okay, can you see that even though the gradient is negative, okay, if we just do it slowly, can you see that the gradient is actually increasing? Okay, because it was kind of steep there and negative, and it's getting shallower, isn't it? And then it suddenly becomes it, so the gradient is always increasing there. And then even when I pass that minimum point, can you see the gradient is always increasing again? So can you see for the entire function, if I move from left to right, the gradient is always increasing. It's always getting higher. Okay, the tangent is always increasing in gradient. So that tells us something interesting about this. Okay. That's just a bit of an insight, okay? It just helps us to get a clear idea of what's going on with the curve, okay? So that's just one reason why we find a second order derivative. I'll give you a second reason, okay? But before I do, I'll give you another example in finding a second order derivative. And in doing this example, okay, I'm going to choose different letters. I'm not going to use x and y anymore. I'm going to use letters s and t. And there's a reason for that, okay? So let's write s is equal to, it doesn't have to be that complicated, t squared plus, I don't know, 5t plus 6, okay, that will do, okay. S equals t squared plus 5t plus 6, okay. Something I've not been doing in my videos is using different variables, okay. The reason is because I've been putting some of these as examples on what they look like graphically, okay. That's traditionally why I use x and y, okay? Remember from the work that René Descartes did with the Cartesian coordinate system, we tend to use x and y as the variables. That's predominantly the reason why we use x and y in our differentiation questions. There's no reason why we can't use letters s and t. And to tell you the reason why I've done this, is because s in mechanics is used for displacement of an object and t is used for, yes, time, okay? So in a moving object situation, when you start the stopwatch, so t equals 0, and then 1, 2, 3, 4, obviously it's continuous, so you can stop it at any time period you want, so you can have fractions and decimals and so on, okay? But for any given value of t, you substitute in that value of t, and that gives you what the displacement is. Displacement is how it's actually changed its position from its initial starting point, okay? So when we look at mechanics, we're looking at how objects move, we're looking at how the displacement is changing over time, okay? Let's look at the first order derivative, okay? The first order derivative, okay? The first order derivative is written like this, ds dt, okay? Because what we're doing is we're differentiating s with respect to time. We're seeing how displacement changes with respect to time, okay? Another word for that is, of course, v, velocity, okay? It's velocity. So let me just see if I can just write it, yeah, I'll write it in v there. Because if you remember, average speed is change in distance over change in time. In terms of vectors, when you've got a direction, we say that the displacement, okay, the change in displacement over time gives you the velocity, okay? And that's another way of saying ds dt, change in displacement over change in time, okay? So when we find a first order derivative, we're actually finding an expression for velocity, okay? Let's write down what that is. So differentiate that, you get 2t and then plus 5, okay? So quite quickly, okay, we've gone from what the expression is for a displacement object to what a velocity is. And then when we look at a second order derivative, written like this, d2s dt squared, that is the same as the acceleration, okay? Because acceleration can be defined as the change in velocity over time, how velocity changes over time, okay? And when we differentiate this with respect to t, we're going to get to 2, okay? And we usually use meters per second for the standard SI units, okay? So you can see that when you substitute a value of t into this, you get a displacement in terms of meters. Substitute a value of t into this, you get a velocity, effectively how fast an object is moving in meters per second, and here you get an acceleration. And the interesting thing here is that the acceleration is always constant, okay? So yes, one reason for finding a second order derivative is because it helps us with drawing the graphs, seeing what the function looks like, how it's behaving. But another, has to be said, major reason as to why I find a second order derivative is because it helps us with mechanics and how objects are moving, okay? So maybe you don't need to know all of that now, but like I said, I didn't really want to introduce to you second order derivatives without telling you a little bit about why it is we're having to do this, okay? Well, I'm hoping you found this video useful, okay? And I hope you have a very good day, all right? See you again.